problems. This is from the 2016 AP test. I think it's the international test. Just some quick thoughts. What comes to mind right away on this one? Let u be the x cubed minus 1, right? Would be a nice u substitution. Okay. Number 8. The whole bottom inside of the bottom, I think, right? Let u be the x squared plus 9, d would be x dx, which is setting up there, okay? And then you got some nice numbers to plug in there, okay? What that one? What's the antiderivative e to the x? E to the x. What's the antiderivative e? It's just a number, right? So what's the antiderivative? The antiderivative is 7. 7x. So antiderivative e would be like ex. So this one, right? Okay. Again, our book is, that's one thing I like about our book. I'd never seen problems like that until this book where pi or e is just a number. So the antiderivative is that. Okay? All right. And now it's starting to show up on the gateway test. Here's an area, so they would have you, so this would be one of those cases where you'd have to know what the graph of that looks like right there, right? You'd have to know that the graph of 1 over x looks like that, okay? And then down here in this quadrant here, and then it says c is between 0 and 1, so here's 1 right here. So it says x equals c and x equals 1. So here would be c would be over here somewhere, here would be 1. So this would be the integral of 1 over x from c to 1, right? You'd have to know enough, and I would think about that picture. Now, maybe not. Well, you know it's above the x-axis, whatever, but since they say that c is less than 1, you would maybe know that. So that would be ln x, right, from c to 1, so then ln 1 minus ln c. What's ln 1? 0. So, I'll see this is, again, I've talked about this. Okay, so it looks like it'd be that, but what is that? Which one of those is the answer? Can you do it when you got a number out in front of an ln? Put it in there. ln of c to the negative 1 would be ln of, right? So a lot of little things going on in that problem, right? Being able to set up an area, set up an integral, right? Do that, you'll be able to do that antiderivative, plug those numbers in, and then also some of those properties of log. So we've talked about that before, how they sneak those things in there on you on the no calculator section, okay? Let f be defined by the function 1 over x. Let f be the function divided by 1 over x. What is the average value of the function on the interval? What was average value? Remember the formula for average value? It's the integral divided by b minus a. The integral from a to b divided by b minus a. That was when we guessed where's that height, right? The area, and then there's some rectangle that would equal that area, and the average value would be right about where it's kind of in the middle. And so it was the integral divided by the width of that rectangle gave you the height of that rectangle, which was the average value. Okay, so this would be ln 6 minus ln 4 over 2, but what can we do with ln 6 minus ln 4? ln 3 halves, the 1 half out in front, right? 6 divided by 4 when you have a minus. Okay. You do a few of these multiple choice questions, you think we ought to have an entire class just on properties of natural log, because it seems to show up so much. They just love making you work with natural log for some reason. So anyway, hopefully by the time we get to the final AP test, what are all the values of x for which this is equal to 0? What are all the values of x for which this is equal to 0? What do you think of when you see this right here? Think of the t cubed. I would hope you would think of t cubed as a graph. You can't use x in here because there's an x down here. It's area. And so basically this is saying, well, what left edge could you have? Whoops. What left edge could you have if, and here's x cubed, if the right edge is 2, what left edge could you have that would make that area be 0? Well, what's an obvious one? 2 is an obvious one. The area from 2 to 2 is going to be 0. Well, what's another one? -2, right? -2, you're going to have areas that are going to cancel each other out. So the area from -2 to 2 is going to be 0, and the area from 2 to 2 is going to be 0. Okay? So just a lot of different ways to ask questions about, notice they're all in this no calculator section, right? So all this stuff we've been doing with area function and antiderivatives and areas and stuff like that. Let h be the function defined by this, pi forced x, that's how we're used to seeing it. Sine squared, that's some function we can't do an antiderivative of that. Which of the following is the equation for the line tangent to the graph of h at the point where x equals pi fourths? The line tangent to the graph of h. Well, oh, tangent line, man, we haven't had one of those for a while. What do you need to draw a tangent line? Or to write a tangent line, point and slope. You need h prime of pi force, and you need h of pi force, right? That's what you need. You need those two things. You need a point, you need a slope. Okay, well, what is h of pi force? That'd be the area from pi force to pi force. That's 0. What's h prime? Oh, we got to do the derivative of this. What's the derivative of that? Sine squared x, right? Not sine squared t, but sine squared x. Do the derivative of the antiderivative. They cancel each other out. Well, that's just sine squared x. Now we plug in pi force. Remember, that's sine of pi force, and then all squared. Well, sine of pi force is root 2 over 2. Square that, you get 2 fourths, or 1/2. 1/2. Now we got it. Now it says, which of the following is the equation for the tangent line? Okay, so y equals the slope times the point, right? And then just figure out which one of those, I guess it'd be that one, wouldn't it? Right there, right? Okay, so, you know, just to kind of brush up on these kind of things as we go along, remembering what we did earlier, chapter 5, with area functions, stuff like that. Okay, all right, let's move on to, well, let's just move on to this stuff. Okay, so we talked last couple days about the definition of a Riemann sum, which is just what? What do you think when you hear Riemann? Rectangle areas. Sum means, of course, adding up. So rectangle sum. Riemann sum is rectangle sum, adding up rectangles. Okay. Here we could add up left rectangles, we could add up right rectangles, we could add up midpoints. These three are Riemann sums because they're rectangles, and then we could do trapezoids too, which really is just an average of left and right. And that's a formula we'll actually use when we get to chapter 6. Trapezoids are really just an average of left rectangles and right rectangles. If you draw a left rectangle and that's here, and you draw a right rectangle and that's here, the trapezoid is just the average of those two. Okay, pretty simple. So, but it's not, technically it's not a rectangle sum. Okay, yesterday we came up with this. This was our big wow moment yesterday, is that the definite integral is the limit of adding up rectangle areas. So you add up how many rectangles to get the exact area? Infinite number of rectangles, right? To get the exact area under a curve is equivalent to adding up an infinite number of rectangles, Riemann sum. So left rectangles, right rectangles, whatever. Now, one of the little technicalities of the definition that I didn't talk about yesterday is on page, you don't have to turn to it necessarily, but it says that let a function f, so this goes with this statement right here. It says let a function f be defined on the interval a, b. The integral, if one exists, to which all Riemann sums tend as n tends to infinity and as the widths of all subdivisions tend towards 0. Okay, as n tends to infinity and the width of all subdivisions tends towards 0. Now, you would think those two would go together, right? We talked about that yesterday. As you go towards an infinite number of rectangles, what happens to the width? smaller and smaller and smaller, and as you go to infinite number of rectangles, you end up with zero width. They just, right? And you get the exact area. That's only true if you're doing equal width rectangles. Remember that picture I did yesterday that they were unequal width? I mean, so you could imagine a situation, matter of fact, let me pull that up real quick. You could imagine a situation where you had, okay, imagine a situation where these three rectangles over here and these two rectangles over here on the right all started dividing in half, right, and doubling, right, and this big fat one right in the middle just sat there and stayed there, right? So if we kept cutting these in half and half and cutting these and cutting these and cutting these and cutting these, wouldn't we eventually have an infinite number of rectangles, right? Couldn't we go towards infinity? We could keep doing that while this fat one just sat here, right, and didn't move. And you would still have an infinite number of rectangles, but it would not give you the exact area, right? So they have to add in that last little bit where they say the n goes to infinity and the width of all subdivisions goes towards zero. Okay, so again, if we're dealing with equal width subintervals, then that's not really an issue. So I'm not going to make you discuss that or anything. Just understand that's why they throw that in the definition. So it's usually good enough for us to just say we have an infinite number of rectangles, we get the exact area. Okay, but technically, there could be a situation where you have an infinite number of rectangles and it's not the exact area because the widths don't all go to zero. Anyway, and so this is what it's made up of, and so the sigma does the adding. This is rectangle height, this is rectangle width. We can kind of see how f of x and dx kind of represent height and width in there, and we can kind of think of the integral symbol as an adder, as an adding machine, and we will see that in our problems that we do, how we use the integral as kind of an adder. We gave the example of if you have a function that's miles per hour, it's kind of like the dx is hours, and it's like what you're doing is adding up a bunch of distances that the car has traveled from point A to point B. Okay, is kind of what's happening there. Okay, but we also have the idea of antiderivative. We know miles per hour, do the antiderivative as miles, and we still get that same scenario. Okay, one other thing I wanted to mention from yesterday, we had this idea of rectangle heights, and we did 4 subdivisions from 0 to pi, and so they were pi force wide, and we set up our right rectangle like this. What if we would have done left? What if we would have done left rectangles? What would have been my first left edge? 0. What would have been my next one? Next one? And the last one? What would the last one have been? 3 pi fourths. Now, how could we have written our sigma with that one? Because remember, this was I pi, so this was 1 pi fourth, 2 pi fourths, 3 pi fourths. Now we're going 0 pi fourths, 1 pi fourth, 2 pi fourths, 3 pi fourths. Yeah, the best way to do it would be to just do that. And wouldn't this be exactly the same? Wouldn't this do it right here? Keep all this exactly the same and just go 0 to 3 instead of 1 to 4? That works every time. That works every time. Right rectangle, if the right rectangle is 1 to 4, then just keep this exactly the same and then go 0 to 3. And that's left rectangle. Okay, so we talked about how sometimes it might be to our advantage to start the I at 0. Well, that's why. Okay, matter of fact, what you're going to notice today is we're going to be confronted with some sigmas, and we're going to turn those into integrals. Okay, we're going to look at a sigma. We're going to say, what integral did this come from? See, yesterday we went the other way. I think that's what we're doing today. Hang on, maybe I should check my notes. No, we're going the other way. We get that complaint. What we're gonna do today is just what we did in that long process yesterday, except for it's a bit quicker. Okay, we're gonna start with an integral, and we're gonna say what sigma would create that area. What sigma would create that area, right? That's what we did. That whole long process yesterday was to get to that. We started with an integral, and then we went boom, boom, boom through this, and we got the sigma to create that. So we're gonna go from an integral to its equivalent sigma, because right back here it shows that they are equivalent, right? So this integral has what sigma that goes with it, okay? And so the idea being that if you have left rectangles, don't do anything different, right? If you're doing left rectangle sigma, don't do anything different than we did the right endpoint sigma. And now midpoint might be a little trickier, so we'll deal with that, and we won't do a trapezoid one. So we'll have left, right, midpoint. So for left, do the same thing you did with right. So look at it, but just say I'm going to start my I at 0 since it's a left. Okay, so if I had 10 of them, I'd go 0 to 9. If I had 100 of them, I'd go 0 to 99. Right? That would make 100. Okay. All right. We'll get into that here in a minute. All right. So let's take a look in your book. So actually, it would be good to turn in your book and look at page 355. So page 355, because our homework's in the book today anyway. So. All right, so we talked about unequal intervals, or what we would do if we didn't have equal widths, or we also talked about how your function, your f of x could be a graph, your f of x could be an equation. We've done both of those actually, and your f of x could be a table. So let's look at that scenario where our function is a table. So, so here's our function f, and 25 says estimate. Okay, so this wouldn't be a bad thing to write down here or to think through anyway. It says estimate this integral from 2 to 5 using a left sum with 3 subintervals. Okay, so let's take this integral and write that as a left sum. Again, this is another thing I'll do probably next week, maybe sometime, maybe on Thursday. But is show you some AP test questions with tables. They love to do things here lately with tables of data. There's almost always at least one AP test question. I'm going to go over one from 2016 here in a minute. There's always, lately here, there's been one free response question that gives you a table as the function, okay? So we want to do an L3, okay? Well, what's the first thing we do? What's the first thing we did yesterday? If we want to write an R4 or R100 or whatever, what do? Find delta x, the width. We find the width. It doesn't matter. It doesn't matter what the function's given as. It doesn't matter if it's an equation. It doesn't matter if it's a table. It doesn't matter if it's a graph. You still kind of go through the same process. Now, yeah, there's a few tweaks along the way, but you just can't, people will look at this and just blank out and all of a sudden start thinking about the table and, oh my God, what am I going to do? You really do the same kind of thing. You say, okay, delta x is going to be 5 minus 2 divided by 3. So that's going to be 1. So our width is going to be 1. Okay? So now we can imagine, we can even do what we were doing yesterday. Here's 2, here's 5, here's 3, here's 4, right? We could make our little x-axis here for our thing. So our first left edge is going to be where? At 2. So L3 is going to be what? What am I going to write? F, very good. F of 2, right? I've indoctrinated you. We're doing F notation. I didn't care that this is a table of I ain't thinking about that other than it's called F. That's about all I care about. F of 2 times 1 plus F of 3 times 1 plus F of 4 times 1, right? I don't care if that function's an equation, it's a graph, it's a table, doesn't matter, it's called F. I've got equal width intervals. I'm going to go, my width is going to be 1 because the integral goes from 2 to 5. So I'm going to say, okay, the width is 1. My first left edge is going to be 2. So I'm going to start there since these are lefts. And now I would say, oh, what's F of 2? Oh, I have a table. Wow, look at that. Okay, it's 0.21 times 1 plus 0.28 times 1 plus 0.36 times 1. And then I add those up. 49, what? That's not right. 49, 70, 85. 0.85. Right? That's it. That's it. Now I could plot those points. It's a lot like the very first problem we did when we entered Chapter 5. We plotted some points. We talked about left rectangle, right? You can do all that. It's going to get to the point, hopefully it gets to the point, one of the things we're going to do on Friday, I'm going to be gone Friday, I think I said that, you're going to have work day on a new AP packet, but also packet just on tabular reasoning, tables of data, given tables, and how you work those problems. And so once we get through that, hopefully you get to something like this. You'll just say, oh, okay, we're going from 2 to 5, 3 subdivisions, so that's 1, that's 2, that's 3. They're one wide, and so I'm going to start at the left, so it'll just be this, plus this, and you'll just look at it and add it up. And you won't even necessarily think about writing all this down now, in doing that, by the time we get to the AP test and so forth. But as far as, let's say our next quiz, and I say, here, here's this function, write out an L3, I want that written out, right? Because I'm saying to write out an L3. F of 2 times F of 3 plus F of 4, like that, and show that, okay? So then 26 says, do a trapezoid sum, okay? Okay, 26 says a T3. Well, we're still going to have the same width over here, but now a trapezoid looks a little different, right? Again, we're still going from 2 to 5. Okay, so what's a T3 look like? Well, what would be my first trapezoid? We're still going 2 to 5. So it'd be F of 2 plus F of 3 times 1 plus 1/2 F of, remember we reuse that, so it'd be F of 3 plus F of 4 times 1 plus, we should have 3 of them, so there should be one more, F of 4 plus F of 5 times 1. Again, we're just going back to this, what we wrote out yesterday, right? That's what a trapezoid looks like. So hopefully starting to get more familiar with that terminology. So now F of 2 is 0.21, that's 0.28. This is 0.28, this is 0.36, and this is 0.36, and this is 0.44. And then we would add those up and do those calculations, right? Now this might be a calculator one, but I don't know. I might, the next quiz, remember that next quiz is going to be Tuesday of next week. The quiz may be no calculator, and you just have to add those up, right? I mean, I'll keep it fairly simple, so you might just add up those decimals, so you should be able to do that, I hope, without a calculator. It just depends how many I give you. I haven't decided for sure on that, but so it might be no calculator, and you just add those up. All right, let's do one more. Let's look at number 28 there. 28 says midpoint. We kind of shied away from the midpoint, but the midpoint's not awful. Notice, though, that the midpoint one, they change it. They go from 3 to 5, and they say to do 2 subintervals. Okay? All right, well, what's my width? Well, now it changes. Now it's 5 minus 3 divided by 2, so it's still going to be 1, I guess, isn't it? Still going to be 1. Oh, it's 1 to 5? Oh, yeah, that wouldn't have worked. Let me show you why my eyes are going bad. Let me show you why that wouldn't have worked anyway. So if we do a width of 1, let's say that would have been 3 to 5, and we say, well, it's a width of 1. Okay, so that means I have a subinterval from 3 to 4, and I have one from 4 to 5. Well, where's the midpoint between 3 and 4? Well, it's 3.5, but what's the value? What's the function value, 3.5? You don't have it. So when you have a table of data, you're always limited. If you want to do a midpoint, you got to make sure you got a point there. And so that's why you do fewer subdivisions. So that's why on, well, actually on 27, they did it with 2 also. So anyway, we go 5 to 1. So this is going to be a width of 2. Okay. So again, I might draw my x-axis. I got 1, I got 5, and so we're going to have a width of 2. So we're going to have our 2 subdivisions. So what do we need? We need a midpoint there. We need a midpoint there. Right? So what is that? I said we're just going to go F of, remember I did F of M1? What's your first midpoint? You just got to think, okay, what's my first midpoint? Well, it is 2, right? So my first subinterval is going to go from 1 to 3, from 1 to 3, and so I'll be right here at 2, and I'll be right here at 4. Those are going to be my midpoints. So F of 2 times 2 plus F of 4 times 2, right? Because my width is 2, and my midpoints are at 2 and 4. But again, drawing a little x-axis right down here can help you to see that. Okay, so that'd be 0.21 times 2 and 0.36 times 2, and add those up, and there's your M2. Okay, so pretty straightforward with tables of data as well. All right, let's go to one other problem that I've got here. All right, so, and again, I think writing some of this down, it's up to you. We're definitely going to have some of these that you have to do in your packets and so forth, but I didn't print this out. But this is from the AP test 2 years ago, in 2016, and this is the actual AP question from the regular test that our students took. Okay, water is pumped into a tank modeled by this rate, W. Okay, so water is going in, and that is liters per hour, right? Key thing to think about. Water is removed at a rate modeled by R liters per hour, where R is this table, and it tells you R is differentiable, so it's not going to do anything crazy, no sharp points or anything. So it's smooth, and it's decreasing from 0 to 8. So we know that it's going down that whole time. So everything's nice, like we would think it would be with those values. Selected values are shown in the table above. At time t equals 0, there are 50,000 liters of water in the tank. Okay, so we're not going to do part A, but just tell me real quick. So they want to know R prime of 2. What would you do? Do a slope between 1 and 3, right? This is the R function. We want R prime, that's derivative, so that's nothing we've been talking about here lately. That's old stuff. We would just do a slope calculation. So we do 950 minus 1190, 3 minus 1, show your, okay? But here's the one I want to talk about. Use a left Riemann sum with 4 subintervals indicated by the table to estimate the total amount of water removed from the tank during the 8 hours. Okay, so now think about this. Is that true? Is that what a Riemann sum would give you, would be the total amount of water? What are the units on R? Liters per hour. If we do the area, remember, when you do a Riemann sum, you're doing an area. You're doing an integral, aren't you? When you do a Riemann sum, you're estimating an area. So it's like an antiderivative, right? So if R is liters per hour, you do a Riemann sum, you're finding liters, right? Your graph would be liters per hour tall and hours wide. That would be liters, right? From 0 to 8. Okay, so what would we do? Well, what's our width? 8 minus 0 divided by 4. So our width should be 2. Oh, wait a minute. What's going on? How can we have a width of 2 when this one goes from 0 to 1 and this one goes from 3 to 6? 99% of the time, we're going to have equal width. This is the 1%. We can't do equal width. We can't go 0, then 2, then 4, then 6, because we don't have those values. So we're stuck going here, but don't we have 4 subdivisions here? Aren't there 4 subdivisions? What are they going to be? They're going to be from 0 to 1, from 1 to 3, from 3 to 6, and from 6 to 8. There's 1, 2, 3, there's 4 subdivisions. They're just not going to be equal width. Okay, so we want to do an L4, what are we going to do? We're going to do R of 0 times right? This is where that x-axis comes in handy. We're going to go up here at 0 because these are lefts, and we're going to go over 1. It's 1 y plus R of 1 times 2, right? R of 1, I don't know where that is, and then it's going to go over to 3. It's going to be R of 1 times 2 plus R of 3 times 3. That next one is going to go, here and then over to 6. It's going to be 3y. And then R of 6 times 2, right? Now, on the actual test, you wouldn't have to write R of 0. I like it if you were in such a habit that that's what you did. But you could actually write 1340 times 1 plus 1190 times 2 plus 950 times 3 plus 740 times 2. You could do that because that's what you're going to do next, right? But that's how we would handle a Riemann sum where there were unequal intervals And we're forced into unequal intervals because of the data in the page. Okay? That's what we would do. All right? And then we're not ready for this next part. Is it over or underestimate? Well, yeah, we would be. Sure, we would be. What did we know about? Actually, my picture's really bad. What do we know about this graph? The R graph's going down. What are left rectangles going to do? If the graph's going down, left rectangles are going to overestimate. So this is something we'll talk more about in chapter 6. But this is pretty simple. So it's decreasing. So this is going to be an overestimate of the total amount removed because the R graph is decreasing. That would be the reason for your answer right there. Okay? All right. We won't go into any more of that right now. We can come back to that another time to do the rest. We can do it. But anyway, I wanted you to see Riemann sum and then also with unequal intervals and how we deal. Okay. So let's finish up here. So a lot of this is going to be like what we were doing. So what we did yesterday, if you remember, we took an integral like this and we using R4 and then R100 and then R sub n, we converted it into a sigma, right? So we want to speed up that process a little bit and we want to practice doing that a little bit. So let's do that for a couple of problems here and then I'm going to give you some work time. Well, see what's left. We should have a little bit left. Midpoint's the one that takes us a little bit of time. I think that's all we're doing, yeah. Okay, we're going to do this one for R10. Okay, so so we're going to do an R10. So what do we need? What do we need to get started? So we think about all that stuff we went through yesterday. There's only, well, where do we start? What do we do first? Delta x, 5 minus 2 divided by 10. That's going to be 3/10. Okay? So we get our delta x. Okay? We make ourselves a little bit of a x-axis over here, right? Go from 2 to 5. Okay? So nothing new, really, today. I mean, yeah, we did a little bit of seeing, extending maybe our knowledge a little bit, but nothing really new today. We want to write a sigma for 10 right rectangles. That's our goal here. Write a sigma that would represent adding up 10 right rectangles. That's what we're doing. So from 2 to 5. So what would be the next one over? 2 3/10. So here we got to make a decision. Do we want to write that 2 3/10 or do we want to write it 23/10? Totally up to you. I don't care how you do it. I would write the next one though as 2 6/10. I would not reduce that. Okay, and then what would the last one be if we're going to write it like this as a mixed number? We do number 2? Yeah. Let's go into this room. All right, how would you write this last one? 2 and... Wouldn't it have to be 2 plus 3? So then it'd have to be 30/10, right? Now, if we did it the other way, this would be 20/10, and then 23/10, and then 26/10, and then what would this be, 50/10, right? So I don't care. You're going to see it both ways, so it's probably good to look at it both ways, maybe. Okay, so anyway, what's my first right? 23/10, or 2 3/10, right? And then times the width of 3/10, right? Then what's my next right? You probably only need a couple to get the pattern. And then I like to put the last one just as a double check. So the last one was going to be 50/10 times 3/10, right? Height times width, height times width, height times width. So again, it's just a matter of what is the width. Write down your x-axis over here so you see a few of them. What's the first right if we're doing rights? The first right is that. Okay, and now, what did we do after we did this? We wrote the sigma, right? We said, okay, what's the pattern? So this is going to be 1 to what, probably? 1 to what? No, careful now, Okay, now, so we're extending our knowledge of what we did a little bit, and now we've got to really work on some of the minor details that can get confusing here. Because we know the integral goes 2 to 5, but that has very, very little, almost nothing to do with what these numbers are, right? This number is what? How many things we are adding up. The sigma adds up this many terms. How many are we adding up? 1, 2, 10, right? Remember yesterday when we did R4, that was 1 to 4. When we did R100, it was 1 to 100. When we did Rn, when we did n rectangle, it was 1 to n. Okay? Doesn't have anything to do with the 2 to the 5. Okay? So this is 1 to 10. So if we're doing it right, it should be 1 to 10. When we do it left in a minute, it's going to be what? 0 to 9. Okay? All right. So now we just need the pattern. Well, every one of those terms has an F. Every one of those terms has parentheses. Every one of those terms has a 10 on the bottom. Every one of those terms has a 3/10 here. Now, yesterday we had a 1 pi, a 2 pi, a 3 pi, so that was I pi. Well, now what we have is a 23, a 26, a 29. We need to generate that. This is where your work in advanced math comes in, where you had to generate these terms. Well, if you go 23, then 26, and 29, you're adding what? 3. That makes you think of 3i right there. Okay, so how can I generate 23 if I have a 3i? 20 plus 3i, that's exactly right. 20 plus 3i, so that'll give me 23, and then it'll give me 26, and then it'll give me 29, and just to double check, we'll go to 10, and that'll give me 20 plus 30, which is 50 over 10, and that's what I want. Okay, so again, what's your thought process? 23, 26, 29, you're adding 3. That means there's going to be a 3i in it, and then you adjust it to get it. Now, what if we were doing 2 and 3/10? Then we would do f of 2 plus 3i over 10. It would have looked like that. 2 and 3/10 means 2 plus 3/10. So we would say, okay, everyone, we have a 2 and 3/10, a 2 and 6/10, a 2 and 9/10, a 2 and 12/10, right? We got a 2 plus something. How do we generate the 3, the 6, the 9? Oh, that's 3i. So we have 2 plus 3i over 10. Well, if you split this apart, you can see you get the same thing, right? 20 over 10 would be 2 plus 3i over 10. So it's the same thing. So I don't care which one of those you do. It's totally up to you. But see how that's going to generate that? Okay, now what was the next thing we did? What was the next thing we did? We took it out of F notation, right? German shorthand. 20 plus 3i over 10, f of 20 plus 3 over 10 means take that and plug it in for x. So this is going to be sigma, I equals 1 to 10, and it's going to be ln 20 plus 3i over 10 times 3/10. Now sometimes in your book, you will see the 3/10 pulled out in front of the sigma. When you see that, you can just say, oh, that's the width. Yeah, there's a 3/10 out in front, that must be the width. Because we can do that. We can pull out a constant. So sometimes we do that. I like to leave it in because I like to see f of x dx. I like to see height and width. Okay? But there you go. That's it. That's the sigma that would add up 20. Now, I didn't do I made a mistake here. I have a horrible, horrible mistake here that should really be bothering you. Well, no, I guess not. No, I didn't. I didn't make a horrible mistake. I thought my horrible mistake was having an equal sign right here. I did, because I said this is R10, and that equals that, which equals this, which equals that. That's true. Here would have been the horrible mistake. If I would have said this equals that, that would have been a horrible, horrible mistake. Why? Because this represents what? This represents what? Use the word area. What? Use another word in front of the word area. Starts with an E. The exact area. This is the exact area. And what is this? Why is it approximate? How many rectangles is it? That's only 10 rectangles. So this is an approximation of this area. If we would have done limit as n goes to infinity, all that would have been the exact area. Okay, so we wouldn't want to use an equal sign there. We want to use an approximate. Just so you understand, this is 10 rectangles added up. That's what we just created. Okay, now we're going to do 10 left rectangles. What are we going to do? Done. Done. There's 10 left rectangles right there. 0 to 9. right? Because now what would happen? Your first one would be at I would be a 0, and so you'd have 20 over 10. So you'd start at F of 2, which is your left edge. And your last one, when you put a 10 in, you put a 9 in, you'd have 20 plus 27, you'd have 47 tenths. Well, if you look, what's going to be the one right before 50 tenths? 47 tenths, right? That'll be the one right before, and that's where your left stop. Okay, let's do the midpoint. Let's do the midpoint. So we just did the left, so that's easy. So once you do, so if I'm doing a left to start with, I just do it just like I was doing a right. I just realize when I write my sigma, I'm going to start at 0 when I'm doing a left. Okay, let's do 10 midpoints. Okay, so everything's pretty much the same, 2 to 5. We've got, we'll just do midpoint here. Our delta x is still 5 minus 2 over 10. So our width is still 3 tenths. So my subinterval is still going to be 23 tenths, and then 26 tenths, all the way to 50 tenths, right? This is 20 tenths to start with, okay? All right, so that's all the same, okay, until we get to here. What's my first midpoint? Oh, it's right there, right? Well, what's halfway between 20 tenths and 23 tenths? No, you can't do 21 and a half tenths. So what do? You double these. You say, okay, this would be 40 twentieths and 46 twentieths. So what's halfway in between? 43 twentieths. So this is going to be 43 twentieths times a width of 3 tenths. Okay, big hint for what we do later in the week. Whenever you see this, when you see the thing inside here has a fraction that is double the bottom of the width, what do you think right away? Midpoint. So here's your big tell what's going on. If it looks like just a normal nice sigma with widths matching up and the I goes from 1 to 10 or whatever, that's right rectangles problem. If it goes from 0 to 9 or something like that, then you got left rectangles. And if you see something like this, where you've got the thing in here has a fraction, is double what the width is, that's because we had to get common denominator, or we had to do this business with our fraction so we could get a midpoint. Okay? And so that's going to be a hint that it's a midpoint. Now, it's not a big deal, right? It makes it a little trickier to find these, okay, but not bad, okay? It's just not going to be quite as obvious. What's halfway between 23 tenths and 26 tenths? Well, that's 46 twentieths, and that's 29 would be, not 29. Yeah, 46, or 23 and 26, so that'd be 46 and 52 twentieths. What's halfway in between there? 49. Now, once you get a couple of them, you see the pattern. Oh, yeah, it's going up. Well, how far is it from 43 twentieths? How far is it from 43 twentieths to 49 twentieths? 6 twentieths. Oh, that's 3 tenths, one width, right? From one midpoint to the next midpoint, it should be one width apart. So actually, I wouldn't have had to do this again. I could have said, okay, from 43 twentieths, what's my next midpoint? Oh, I just got to go over 3 tenths. Well, 3 tenths is 6 twentieths. So from 43 twentieths, I have to go to 6 twentieths. I have to go 6 more twentieths, so that's 49 twentieths. And then the last one, I a lot of times don't get the last one on midpoint. I get the last one as kind of a double check, but it's kind of tricky to get these. And so I'm kind of like, yeah, maybe it's probably not worth it. It's kind of a double check, but probably don't need it. I think getting a couple here is enough to generate it. Okay? So what do we need? Well, the midpoints usually go just like rights. They go 1 to 10 are usually the easiest. Okay, we got our F, we got our parentheses. We notice that everyone has a 20 on the bottom, has a 3 tenths out here. So all we have to do is generate that top number. We have to generate the 43, then the 49, then what? Well, what do we notice we're adding each time? We're adding 6, so there's going to be a 6i involved. So how do we get 43 with a 6i added on? How much? 37 plus 6i. We can't start at 40 because that would give me 46, right? I need to get 43, right? So I need to get 43, and I have to add on the 6i, right? So I need 37 plus 6i. Now I can check that, put a 1 in, I get 37 plus 6, I get 43 20ths, put a 2 in, I get 37 plus 12, which would be 49 20ths. If I want to check the last one, I can, but I didn't write it down, so it would be a great double check. Because the last midpoint, look, the last midpoint is half a width from there. Well, what's 50 tenths? That's 100 20ths. Half a width is 3 20ths, right? The width we said was 6 20ths, so half a width is 3 20ths. So it's going to be 97 20ths. That's what the last midpoint will be, 97 20ths. So we put a 10 in here. We're going to get 60 plus 37. Oh yeah, 97 20ths. Okay, so that'll give us our last one. So I don't know if that's a huge deal to figure that out, the last one. But it's half a width away. Remember, because it's midpoint. So it's half a width away from 5. Okay, so there we go, and then the last thing to do is just put it take it out of our F notation, so we'd have ln of 37 plus 6i over 20 times 3 tenths, and then we got I going from 1 to 10. So midpoint, a little trickier in that you have to work with fractions, okay, so that's about it. But there will be kind of this mismatch usually in the fraction here because of the midpoint scenario. And that's what we're going to do. So a lot of our homework is looking at that. Start with this integral and then write a sigma that represents that. Okay? All right. So 5.7. I was gonna help you get started on 13 because it is another midpoint one. So I was gonna. Is it a midpoint one? Oh, because of the multiple parts. Yeah. So 13, 14, 19, 20, they're very similar kinds of problems. So I was going to help you get started on number 13 here. So let's there's multiple parts to these, but the multiple parts are this. They tell you to do, on 13, they tell you to do a right sum with 10 subintervals. So they tell you to do an R10. Then they tell you to do an R5, an R20, and an R50. Well, once you've done the R10, the others are pretty easy. It's just the width changes, and you can just make some minor tweaks. It's not like you have to redo the whole problem. Okay? So this is page 362. All right? So we have the integral from 0 to 10 of x squared dx. Okay, it says use sigma notation to express the right sum approximation with 10 subintervals. So we're going to do an R10. Okay, and then I'll help you. I'll show you. Okay, now what's it look like to change that to an R5 or whatever. Okay, so what happens? What do we do first? Delta x would be 10 minus 0 over 10, which is 1. Well, that's always nice. We're not going to have fractions. Okay, we'll do one with a fraction here in a minute. Okay, so we get 1. So the width is going to be 1. So we maybe make it x-axis. It's going to be 0 to 10. It's going to go 1, and it's going to go 2. So, okay, you have to mess with fractions too much. We've done so many with fractions, almost makes it harder. We got to think about it. Okay, now it's rights. It's rights. So our first right is going to be f of 1 times 1 plus f of 2 times 1, and the last one, f of 10 times 1. Okay, so that's going to give me a sigma of, right, this is going to go 1 to 10, because we're not because the integral goes 0 to 10. Remember, this has nothing to do with the 1 to 10 here, right? We're doing an R10. That's why we're doing 10 rectangles. That's why it's 1 to 10. Okay, so what's this going to be? F of I times, doesn't get much easier than that. Take it out of F notation. What do you got? What's f of I? Plug an I into the function. You got I squared times 1. I equals 1 to 10. Okay? So sometimes they can be quite simple. And actually we have a summation formula for that. We could actually do a quick calculation of those 10 rectangles. They don't actually do it, so don't worry about it. Okay, but we have that I squared summation formula. Okay, what I wanted to show you is, okay, now what happens when it changes to R sub 20? Okay, how much more work do you have to do if it changes to R sub 20? Well, you have to do a fair amount, you know, but you can get pretty quick at it. I mean, you're still going to do your width, right, which is now going to be a half, right? So your width is 10 minus 0 divided by 20, so your width is going to be a half. When you go on your number line, you got 0 to 10, and you're going to have 1 half. I would go 2 halves. I would go 3 halves, right, all the way to 20 halves, I think, is how I would do the number line. So you do make that. And then, and at this point, if you know, just write out a couple. So your first right is going to be f of 1 half times a half plus f of 2 halves times a half, right? That's probably enough to see it. You can go all the way and write the last one. But, so what's our sigma? I equals 1 to 20, right? We're doing an R20. We're adding up 20 rectangles. So the sigma is going to go 1 to 20, okay? And then this is going to be f of, it's 1 half, 2 halves, 3 halves. So that top number is just I. So it's I over 2 times a half, okay? And then you can write it, and then you can go from there and just be I over 2 squared, right? I over 2 squared times a half, and I goes 1 to 20. Okay, so as you see that, now you do the one with 50, you know, you can probably see, well, what's it going to be? Now it's going to be 10 minus 0 over 50. It's going to be 1/5. So it's going to be 1/5, 2/5, 3/5. So you can probably see, well, all that's going to change is those halves are going to be fifths. And you know, and that last one, you can probably just write it down. You can probably just write what it's going to be without writing out all the little pieces as you go. So I know I'm so on 13, 14, 19, 20, I think on those 4, you have those 4 parts, but it's good practice to be able, and even 23, I guess, it's good practice to see one and then, you know, be able to do a little more of it in your head maybe and so forth. By all means, write it out if you need to. But we really want to get it to where we can imagine these subdivisions, we can imagine the rectangles, we can do height times width, put it into a sigma pretty easy. Okay? All right. So the rest of the time you can work on those. At the end of the day, you know, if I ask you, because on the quiz we'll do a couple things. On the quiz I will say, write out 10 right rectangles. And then that's what I'm going to want to, and the rule's going to be this. And it won't really be a big deal on this quiz, but future, if there's 10 or fewer, we're going to write it out. If there's like 20 or 30, you know, we'll do a sigma, we'll have a program in our calculator, we'll let that get calculated for us automatically. So on this quiz, it'll be more about writing it out. So I may not do 10, I might, but that'd be the most, where we would write it out. You know, I want to see the f of da-da-da-da-da, I want to see that all written out. Okay, and then maybe evaluate it. If the problem is just to write the sigma, right? If the problem, like these are, is to write the sigma, then how much of this you write out is up to you. Write out as much as you need to be able to figure out what the sigma looks like. Now, I've given you, my suggestion is, you know, when you write it all out, you can see the pattern easier and it helps you write the sigma. But once you've done a number of them, you get better at it and you can start to write the sigmas without maybe writing as much out. So that's okay.
If you can do that, that's okay.